Today I'm just going through the modeling and simulation of dynamic behavior of elevator system, which we will did, and we will still is an ongoing research for ourselves in University of Northampton. A bit of the outline, background and introduction, problem formulations, computer modeling and simulation, which will talk about the stage of the research which has been taken, demonstration of computer simulations results, and hopefully at the end, conclusion and the further works of this work. Vibration phenomenon is taking place in the lift and hoist installation, which might affect all the performance of all the other components too in the elevator system, and it will obviously related to the quality, ride quality of the lift car. Longitudinal vibration of a ceiling and the car may result in adverse dynamic behavior of the entire installation. For this reason, we will require a comprehensive model to be able to, for the showing the all coupling and linear system in the lift simulations, and predict and eliminate the unwanted resonance in the, which will affect the ride quality and structural integrity. The reason that for using the dynamic multi-body dynamic system is because in the region of the design, it will play a very massive role for every managers and every design engineers, because we can actually reduce the cost and the time of the produce and production lines quite massively. Quite traditionally, I just really like these slides myself, so I thought just to share it for you in a few minutes. Traditionally, what we're coming with from the concept, we go through the all passage of the design, detailed design, we produce it, and verification, which will come in terms of the evaluation and make sure that analysis will be answered properly. But as you can see, if we are not happy at this stage, we have to keep repeat all these procedure, which will cost us the money and time of the product, and I know the time is most valuable aspect for every engineers and every manufacturers. So the new development will always passing into the analysis of the software and prototyping and simulation actually. Even though that we might not want to spend, we have to spend some time for the simulation part, but in this section we can make sure all the aspect of the design has been looked at it, and the best options, the best concept, the best design is going to be sent into the detailed design, prototyping, and production, and mass production later on. Just a bit background in terms of the multi-body dynamics, and I'm sure everyone here will be familiar with these terms, but just for reminding ourselves, is the multi-body system is consists of solid bodies, and they've been connected by the joints, and which will restrict their relative motions. This study can actually show the mechanism under some influence of the force or vice versa, which that brings lots of problems. To solve these problems, we need to make sure as we have inverse dynamics. It's important because the product design frequently requires an understanding of how multiple components are acting into each other and toward each other and interact with each other. Elevator is not an exception. Elevator or escalator, all of this system has been developed by the multi-body dynamics too. So in the vertical transport, we can use very easily multi-body system. Vibration of elevators components may influence the dynamics behavior and the performance of each component during the runtime. And obviously it will be affecting the quality of the ride quality. I tried in this paper to present a theory of the multi-body dynamics, including the simulation, to match the mechanical models of the elevator system, which can be used to understand the condition monitoring and the operational parameters in much faster and much easier way in terms of the performance of each component and simulation. So for problem formulations, very simple case, we can have the rope system, the sliding and the frame and the car himself, which can actually very easily be transferred himself into the mathematical model, which then we can have the mass of the both section, which can be included into 2 degrees of the freedom, with including the 2 different type of the spring stiffness on the side. And it can be easily be transferred himself into the motion equations. The M and K will be represent himself as a mass and a stiffness matrix in here. And I might mention that the NR in here is the number of the rows, which is in my case the number of rows would be number 4. So if you put the equation of the omega, which will represent himself as a frequency, and X will represent himself as an amplitude of the vectors for the modes, in my previous equation number 1 in here, we can just simply simplify the equation into the current part. And if you take it with the integration part in a bit later, we're coming up with the frequency and the mode himself in the 2 different cases. And both of these cases can actually represent himself in the mode 1 and mode 2, x1 and x2. So by a very simple case, I tried first to verify the numbers, the numerical solution with the MATLAB, and very simple writing code on the section, putting the parameters which will represent the actual lift, which we will study in this case, we coming up with the main diagrams on the 6th section. You will be noticing that this is for the modes 1 and mode 2, and is obviously in the mode 1, the amplitude of a second mass will be a bit greater than the mass of the second one, and in the motion of the 2 masses are in the same phase. When a system vibrated in the second mode, the amplitude of the first mass is greater than the magnitude have been opposite signs, which means that both will be having the opposite and in the opposite 180-degree direction. This will result in the first mode and the second mode frequency of a 3.1 Hz and 11.60 Hz. We made this model based on the SolidWorks, then I imported this one into the Adams, which is why I'm using it for the multi-body dynamics simulation. And I will representing the force in here, which can be just simply be generated by the simple shaker, or someone just keep jumping upside down into the car. So that's the force can actually be provided to produce the excitation in the car. You probably noticed in my previous section that I had 2 set of the spring on the side and 1 at the top. To make it a bit more realistic in my presentation, I had about 9 spring on this section, 9 on the other one, 2 and 2 on top side, which represent himself in terms of the damping side and damping components. And that's why I just made it a bit more easier, which means the K at the end will be equal with the quarter of each one separately. So in a very simple case, we could actually see all the springs is acting properly, and there was no problem in terms of the frequency. And the frequency is exactly matching the frequency which I had from the numerical solution from the MATLAB. But the main point in my case was, even though that the frequency of these modes are the same, but what they really mean in terms of design and designers, in terms of the actual engineers himself. That's why the multi-body dynamic simulation, such as software like a MATLAB, will tell you that's for example, is a mode 1, and that will be the mode 2. And you can see that in the mode 1, the both frame and the car is actually acting together, which was exactly the same result into the MATLAB part. And in the second mode, the frame and the car is actually 180 opposite, which is exactly confirming the result which we had. Apologize. It's not that easy. You didn't think I'll finish, did you? Which is exactly represent himself in terms of the first and the second and opposite on the both results part of it. In another study, well, maybe it would be better just have it in the dessert. In another study, we also managed to confirm and compare the result from the car velocity, acceleration and jerk times into the MATLAB file, and confirm the same result into the Adams software and simulations too. So in theory, the dynamic behavior, and in conclusion, we can say the dynamic behavior of vibration and elevator system can be predicted by using models and computer simulation techniques in ADAMS, which will give all engineers a better understanding of how the system will be react and will be interact within each other. One of the challenges in the high-speed and high-rise elevator system is the influence of a low frequency source of a tall buildings, which this morning Professor Stefan talked about it, and Rafael is also going to talk about it a bit later. And it will be required that we understand the rope behaviors interacting with each other, which is one of the part that will be the impact of the ropes within each other or ropes with the wall himself, which is one of the would be our future simulation, which we will help of the ADAMS and MSC software. We will try to actually sort that one out. And thank you very much. I would like to thank you, MSC Software, for supporting us during this tough year. And we will enjoy the cooperation for the hopefully next year. I try to make it. Thank you very much.